start.
Hello, my dear students, and welcome back to part 2 of the lab discussion. I stopped and restarted, and unfortunately I'm not very good at video editing or knitting these together, so you're going to get 2 separate ones, but I saw a mistake. Yes, I made a mistake and made an error in my calculations. So, here's what we have to do. We now have these wavelengths, but they were in nanometers. Okay, so we have to convert them all to meters so that we have consistent units. There are 10 to the 9th nanometers per meter. So if I I'm multiplying by 1 over 10 to the 9th, or if I divide that value, that wavelength, by 10 to the 9th, I will get my wavelength in meters, and I get these values. Here's the value for sodium chloride, okay? So sodium chloride, when we did it, it was that orange color that had a wavelength of 609 nanometers. I divide that by 10 to the 9th nanometers per meter. And here's what I get, 6.09 times 10 to the minus 7th meters. Well, of course, the wavelengths of these are extremely, extremely small. And that makes sense. And I do that for each of these wavelengths, getting these values. Save you the trouble if you just copy them from me. But here's the deal. What we want to do next is calculate frequency. So I'm going to continue doing it for sodium chloride, as it says here. Show a set of sample calculations for sodium chloride only below. And they want the frequency. So we'll solve for our frequency using our wavelength and our constant speed of light. So nu, our frequency, I can't make a Greek letter nu, so I just wrote out nu, is equal to c, the constant speed of light, 3 times 10 to the 8th meters per second, divided by lambda. I can't make a Greek letter lambda, so I just wrote it out, but the constant speed of light is 3 times 10 to the 8th meters per second. The wavelength is 6.09 times 10 to the minus 7th meters. Meters cancel. It leaves us with reciprocal seconds, which is what? Frequency, or hertz. And so what we're left with when we do the calculations is 4.93 times 10 to the 14th hertz. So those light waves are very small wavelength, but they come at you very quickly, a lot of them impinge every second. And now, using Planck's equation, which is energy is equal to Planck's constant times the frequency, or nu, we use Planck's constant, 6.63 times 10 to the minus 34th joule seconds, times 4.93 reciprocal seconds, 4.93 times 10 to the 14th reciprocal seconds. The seconds cancel, leaving us with joules. That's a measure of energy. That's the SI unit for energy. We get 3.27 times 10 to the minus 19th joules. If you go through, sit with your calculator and do all these calculations, you will get the following values. You may need to freeze, do a screenshot, blow it up, I don't care. Or ideally sit and calculate all these yourself. But you will get these energies. I want to point out one thing here, and that is the red wavelengths, the long wavelengths like lithium chloride, have much lower energies than the short wavelengths in the blue and the purple. Almost half as much energy as, for example, the purple carries. This is the energy, by the way, per photon. So, not a lot of energy, 10 to the minus 19th joules, but think about how many photons are actually falling, and then it adds up. So, I'm going to move on to the next part of our lab. It asks us to examine the spectra for helium, hydrogen, and mercury. And they show you the line spectrum for helium right here, along with carbon. And when we looked at it, we didn't quite see all of these, but I'm picking out some of the major ones. And there's a purple, a blue, let's see, that's my helium, yeah, okay. So there's a purple, 2 blues, a yellow, an orange, and a red. And it's very easy to look up the wavelengths of those lines, and that's what I did. And they are at 390, 470, 502, 588, 668, and 707 nanometers, with the highest energy down here in the purple. When we looked at mercury, there are a number of lines, but when I looked through our spectroscope, our spectrum analyzer, where we got the line spectrum, I, with my old eyes, could see 3 main lines, so that's what I kept it at. Plus, it's less work to do. There's some more, but in mercury, I clearly saw a purple, green, and orange line, and that purple is at 405, that green is at 546, and I'm not so sure, but the orange, I think I looked it up, it said 691 nanometers. We'll just go with that. That value seems pushed down into the red. I'm wondering if when I looked it up, the book I looked it up in, if that should have been 619, if that was a typo, because that seems awfully long wavelength for an orange line. Show you what I mean with the next one. Oops, I don't know how that happened. In here with the spectrum for hydrogen, there's a number of lines. I want to say we're supposed to see 4, but I saw 3 very clearly. Purple, blue, and red. The purple was 434. The blue, if you look it up, is 486, and the red is 656. You can see orange should not be longer than the red. But those are the values that I got without going into too much detail and research. Now, let's answer our questions, okay? I'm going to pull out this paragraph that says, complete the following paragraph by circling the correct responses. Well, depending on what you're using, if you're using DocCalc, that's fine, you can circle it, but I just have you write it down here. It says, in this experiment, the metal cations in the solution were initially in the ground or excited. Pick one. But I'll just tell you, they're in the ground state. When placed in the flame, the metals then absorbed energy as heat. And when this occurs, the electrons made transitions from low energy levels to high energy levels. The metals were then in the excited state. And the electrons in these metals then made transitions from high energy levels to low energy levels, resulting in the emission of energy as, and they give us some choices, obviously EM radiation or light, but they also shed some of it as heat. So once again, I know a little bit more than the authors do, and they should be a little more precise. So I said and heat with a big capital and. Now, what evidence is there that the colors observed in the flame test are due to the metals and not the non-metals in the compound? When we did this, we used copper chloride, lithium chloride, barium chloride, potassium chloride, etc., and in every case, chloride was a counterion. So if they all had chloride in it, the differences in the color must be due to the metals themselves, and that's what I said. All the metals tested were chloride salts, and thus all had the same counterion, chloride, such that differences in color should be due to the metal ion alone. And I said, which metal ion was observed to emit radiation with the longest wavelength? I tried to talk to you about this. Lithium, with that beautiful red light, had the longest wavelength light. You can see that in the table. And because it had the longest wavelength, it also had the lowest frequency. Okay? Because if you have a big wavelength, you need a small frequency because they're inversely proportional. And if you have a low frequency, you can have a low energy because of Planck's equation. You multiply by the frequency, the lower your frequency, the lower your energy. Simple math. Now it says, why do gas discharge tubes need to be turned on before a color can be seen? Well, the atoms need an input of energy for the electrons to absorb before they are raised to a higher excited state and begin to glow. and you observed the spectral lines for different elements, what is happening within an atom that causes it to emit light in specific lines in the spectrum? Well, the electrons in an atom are quantized in that they move between very specific energy levels that correspond to specific energy emissions when they return to the ground state. That's why we get a very specific color, because that energy is quantized. We don't get a continuous spectrum. We don't ramp up, we step up. And that's the take home for the quantum model of the atom. Now, why do different elements have different emission line spectra? Well, the electrons start out and move into specific but different energy levels that correspond to different energy emissions, and thus different frequencies and wavelengths. Wavelength is just another name for color, so we get different colors. Depends on what orbital they're in and what orbital they go to. So, there's a quick problem here. The radio station, Arkansas, JARC FM, broadcasts at 93.5 kilohertz on your FM dial. You know, you can find that 93.5. Calculate its wavelength, lambda, in nanometers. They want it in nanometers, so we have this value in kilohertz, and that 93.5 kilohertz is 93,500 hertz, and if I use my equation, where the speed of light is 3 times 10 to the 8th meters per second, and hertz means per second itself, then when I solve this equation, my wavelength is going to be equal to speed of light divided by that frequency, which is 3.21 times 10 to the 3rd meters. But they want it in nanometers, and there's 10 to the 9th nanometers. So I multiply this 3,210 by 10 to the 9th, and I get 3.21 times 10 to the 12th nanometers. And using our equation, Planck's equation, once again, I can take that frequency that they gave me before, 93,500, and calculate the energy, Planck's constant, times that frequency, 93,500 hertz, gives me 6.2 times 10 to the minus 29th joules. Not very much, but that's the energy in a single little photon of light. You know, you don't have to worry about the power of radio waves. They're coming through you right now. Unless you get up really close to the antenna where you're getting a lot of that radiation, in general, you don't need to worry about radio waves at this frequency, because the energy in kilojoules even is 6.2 times 10 to the minus 26 kilojoules. 1,000 joules in kilojoule. Do your best, fill in the answers. Remember, this counts the same as a test. So I know it's a lot of work and a lot of effort, and I'm sorry for the people virtual at home who can't come in and do it. If we ever do all get together again, we'll just have a lab party and we'll do all our labs and visualize everything and experience everything ourselves. Have a great Thanksgiving, stay safe, and I will see you in the next video.